In this video we're going to be covering page 42. So let's recall first, an annulus is really just a like a washer. So pretend that's a circle, and we have another circle concentric but removed. We wanted to know the area of the ring essentially, so let's pretend that the outer radius, the bigger circle here, has radius capital R, and the smaller circle has radius little r. Then I think we remember what we found is that the area, so I guess I'll say area here, was pi big R squared minus pi little r squared, because really what you're doing is you're just removing the area of the smaller circle from the bigger one. And if we factor out pi, we get something like this. So r squared minus, like so, right? Okay, so let's apply that to this next problem here. So we're going to enclose the curves, or we're going to find the region enclosed by the curves y equals x and y equals x squared, and we're going to rotate about the x-axis. So we're using washer method class, and we're rotating about a horizontal axis. So that means everything needs to be in terms of x, which they are, right? X squared and x, those functions are in terms of x. So let's see what we get here. So here's 1, and there's a height of 1. Y equals x looks like just a straight line from the origin, and then x squared is actually underneath this on 0 to 1. So this is actually the region we're going to be rotating here about the x-axis. Okay, and so if we draw what we get, we're going to get something like this, something like that, and now what we're going to have is cross-sectional. Now they're no longer discs, they are cross-sectional washers. Okay, so something like that. And so the outer radius class, well, that's the function that's going, or it's going to be given in large part by the function. So let's pretend this is some x value in our range 0 to 1. It's going to be given by whichever function is farthest away from the axis of revolution. And I guess we can use our final color here to show you the inner radius will be given by the one closest to the axis, right? So our cross-sectional area region is no longer just pi r squared, it's going to be pi, and then I like to put a bracket, outer radius squared minus inner radius squared. And using our colors here, the outer radius will be formed by, in this case, the function x, y equals x, and the inner radius is actually going to be given by, let's do this right here, will be given by x squared, right? And now simplifying, this is just pi times bracket x squared minus x to the 4. Okay, now it's probably important that we learn, or at least remember, how to determine where the region ranges from. Now it's, I think, pretty transparent to see that it goes from x equals 0 to x equals 1, but if you really wanted to make sure, we're actually looking for where these two graphs intersect, right? So where the graph of x squared equals the graph of x. You solve quadratics by moving everything to one side and factoring if possible, otherwise quadratic formula. But I think this one factors nicely, and we get x equals 0, x, and x equals 1. Okay, so that means that the volume of this strange looking solid that we get here, I guess you could call it a bowl shape, is the integral on the x bounds of the region, so 0 to 1, a of x dx, which we found to be pi x squared minus x to the 4 dx. Okay. And this is, let's see, pi, and you get x to the third over 3 minus x to the 5 over 5. And now just plugging in 1, we get pi. 1 cubed over 3, I think, is 1/3. And 1 to the 5th over 5 is 1/5. Minus pi times parentheses. And now if you plug in 0, you just get 0 everywhere. So I think we can see that that last part is 0. And the common denominator is 15. So we get pi, denominator 15. Let's think about this. So here we needed to multiply by 5, so we do the same to the top. And here we would need to multiply by 3 to get our denominator, so we do the same to the top. And so we get 2 pi over 15. And I think we did this one in class, so hopefully nothing new is happening here. Okay, now scrolling to the bottom of the page, this is a new problem. We need to find the solid obtained by rotating the region bounded by the curves y equals 1/4 x squared, x equals 2, and y equals 0 about the y-axis. Okay, so because we're rotating about the y-axis and we're going to be using, we're in section 2, so disk washer method, we need everything in terms of y. So this right here, we need to solve x equals a function of y. So if I multiply both sides by 4, I get 4y equals x squared, which now if I take the square root, I get 2 root y, I believe. Okay, so let's see what this looks like. Well, okay, so the line x equals 2 is actually forming a vertical line, and this will be sort of like the right bound of our region. Pretend I made it through there. Y equals 0 is actually the x-axis. And now this function, I think we saw, if we scroll back a little bit, so look back in your notes, we found that at y equals 1, we had an x value of 2. And remember, it made something like a parabola shape. So really, the region that we're rotating is not this stuff in here, but rather this stuff right in here. Okay. And so let's see what we get when we rotate this. Well, now it'll be like a bowl, but with perfectly straight sides, right? And now we no longer have a cross-sectional disk when we rotate. We will have a cross-sectional washer, as we're seeing here, with its own inner and outer radius. Okay, so let's see if we can figure out what that is. So now, for every y value in this range, it looks like it's going to be 0 to 1. The outer radius is given by, now notice it's given by this line x equals 2, right? And that actually does not change no matter where your y value is in 0 to 1. So here is our first big observation, that a of y well, we're going to get outer radius squared minus inner radius squared all times pi. That'll be our cross-sectional washer area. But the outer radius is being formed by just the line 2, x equals 2. Right? Okay, and now we'll switch over to green, and we see that the inner radius is actually being formed by this function x equals 2 root y. So that'll actually go here as our inner radius, 2 root y. And so when we simplify, we're going to get pi bracket 4 minus 4y. And now it looks like we're just going to integrate from 0 to 1 to find the volume of this bowl with straight edges. So integrate 0 to 1. But everything has to be dy here, class. So that's why we're doing the y bounds on the region. So pi 4 minus 4y dy. And what we observe is that the antiderivative is 4y minus 2y squared. We evaluate from 0 to 1. So plugging in 1, we're going to get 4 times 1 minus 2 times 1 squared. Now let's be careful here. So 4 times 1 minus 2 times 1 squared minus plug in 0, which is the bottom number. Sorry, class. It should be pi times parentheses. Plugging in 0, we're going to get 0 minus 0. So I think all of that is 0 when we plug in 0. And simplifying, we get 4 minus 2, which is pi times 2, which we can write much more nicely as 2 pi. Okay. All right. So in the next video, we'll be covering page 43, where we learn how to rotate about axes that are not either the x or the y axis, which is everything we've been doing so far. We did a little bit of this in class, but we're going to go a little bit deeper into it in the next video.